Welcome back to this lecture on set operations. In the second segment, we will introduce two new set operations. First is the set difference of two sets S1 and S2, which is denoted like a regular subtraction, except it applies to sets instead of numbers. So by definition, S1 minus S2 is the set of all the elements of S1 that are not in S2. So in logical notation, it says for all x, x is a member of S1 minus S2 if and only if x is a member of S1 and x is not a member of S2. So again, we'll illustrate this definition with a Venn diagram starting with the universe, a circle for S1, and a circle for S2. So where are the elements of S1 minus S2? Well, they must be inside the circle S1, since they must belong to S1, but they must be outside the circle for S2. And the only elements that satisfy these definitions are the following, and these are in the set difference of S1 minus S2. Now, if we're going back to our usual example for sets with S1 and S2, let's compute the set difference S1 minus S2. The way you do this is you can go through all the elements of S1, and this time you keep all of the elements that are not in S2, as opposed to in the intersection when you would only keep the elements that are in S2. So we're going to go through the elements of S1 one by one. The first one is the empty set. We check that the empty set is not an element of S2, therefore it's definitely in a set difference. Let's add it. Similarly, the singleton set S3 is in S1 but not in S2, so we add it to the difference. Notice how the integers 1 and 2 are not added to the difference because they are also in S2. And so on and so forth. We continue with the integer 4 and the integer 5, each of which is in S1 but not in S2 and therefore belongs to the set difference S1 minus S2. So again, this set, and remember the set difference takes two sets and returns another set. This set contains four elements, namely all of the elements of S1 that are not in S2. And in particular, S1 minus S2 must be a subset of S1 by definition. Now let's compute the set difference of S2 and S1. In other words, S2 minus S1. Again, it's a set, so I can start it with an opening left curly brace. Now, how do you compute the set difference between S2 and S1? Well, this time you start from the elements of S2. You go through them one by one, such as 0, and each one of them that is not in S1, like 0, gets added to the difference. The integer 1 is also in S1, so it does not get added to the difference. Neither does the integer 2. The integer 3 is not in S1, so it does get added to the difference. And the last element of S2, namely this set here, is not in S1, so it's also in a set difference of S2 and S1. And this concludes the computation. So the first thing to notice here is that the set difference of S1 minus S2 is different from the set difference of S2 minus S1. And in particular, we can show that clearly in the Venn diagram. Remember, the Venn diagram we drew up here was for S1 minus S2. So let's annotate that. Now let's draw another diagram, Venn diagram, for the other set difference, S2 minus S1. These are the elements that are within the circle for S2, but are not within the circle for S1. So in other words, it's the set of all these elements. let's label them. And clearly, those two sets in general are different. So the situation is to be contrasted with the earlier set operations we defined, namely union and intersection. The union of S1 and S2 is the same as the union of S2 and S1, and the same holds for intersection. In other words, the order of the operands of intersection and union does not matter, whereas for set difference, the order of the two sets does matter. Now, this being said, let's look at another computation, namely the set difference between S1 and the empty set. What are the elements that are in S1 but not in the empty set? Well, the answer is all of the elements of S1, since you don't get to remove any elements from S1 since the empty set is empty. On the other hand, the set difference of the empty set with S1 is the set of all the elements that are in the empty set. Well, you can stop right there. There are no elements in the empty set, so you can't remove anything, and the answer is the empty set. So make sure you understand this operation completely, and this concludes our example. So let's conclude this segment with our last definition, namely the complement of a set S, which is denoted with a horizontal bar over the name of the set here. By definition, this operation only takes one operand, a single set S, and it returns the set of all the elements in the universe that are not in S. That's the complement of S. So in logical notation, for all X, X belongs to the complement of S if and only if X is not a member of S. Let's again illustrate this definition with a Venn diagram. Now this time we only need one circle for the set S, and the elements of the complement of S are all of those elements that are in the universe but not in S, namely all of the elements outside of the circle but still inside the universe. Now the important thing to realize here is that this operation of complement is relative to the universe. In other words, realize, for example, that the elements that are outside the universe, say over here, these elements here, are not in S, but they're also not in the complement of S because they don't belong to the universe. So again, the complement depends on how the universe of discourse is defined. And another way to define the complement, to make this explicit, is to realize that all the elements in the complement of S are all the elements that are in the universe, but not in S. So in other words, the complement of S is the same thing as the set difference between U and S, or more explicitly, U minus S. Now let's go back to our example and use S1 as our set, and let's ask ourselves, what is the complement of S1? Well, it's all the elements that are not in S1 but that are also in the universe. And since we did not define the universe for this example, we cannot answer this question. The answer depends on the universe. So I'll let you pick a universe for this example and then answer this question for yourself. And this concludes our second segment on set operations.